start. So 5 is asking, and I know I that's why I don't love the textbook, but these are pretty good questions overall, right? So to access an online game, right, it's password protected. You need to create a password that has 2 capital letters followed by 3 digits. Each condition below, for each of the conditions below, determine the probability that a password chosen at random will contain the letters S and Q. Notice the word and. It has to have both, right? It's not or, it's and. So both of them have to be present there. So it's not necessarily cases in that regard. So I'm doing this on page 21. So page 321, question 5. So let's come up with our probability. It's asking for probability. So it'd be our NA over our NU. Okay. I like to focus on NU first. And that would be if I have my setup. So passwords don't use combinations, right? You'll set it up like this. And so since I'm not allowed to repeat, so this is 5A, no repetition allowed, no repetition. So if I have letters, that means I have 26 and 25, correct? And then I have, when it comes to numbers, 10, 9, 8. So almost imagine if I asked you to create a password that cannot have any repetition, this is how you would do it, right? All possible. And the NA is when you have some restrictions placed on you. And the restrictions come up front. So I'll say SQ, right? Those are your options there. And the way I do this is I go 2 times 1, right? You can at first use S or Q, right? You have the choice, and then the other one has to be the one that's left, right? So you can start S and then Q, or Q and S, but you have essentially two cases there. You cannot have SS and so forth. All right, and then the number part, I just do the exact same thing. And so if they don't tell you otherwise, we're assuming it's 0 to 9, which means you have 10 digits. Okay, that's another thing. Letters, same thing, we're assuming 26. So there's your NUNA. I will now set, let's come up with a number. So this is 2 times, if you want to sound smart, right, you just do one of these. Or you go 26, pick 2, times 10, pick 3. You don't have to have this, but I think, you know, sometimes the key or whatnot has that. You could have also written the 2 as 2, pick 2, would have been the same thing. So probability in this case would be, the top gives you 1440, and the bottom gives you 468,000. You check your back and you're like, this is off, right? I don't know. I'm pretty sure they will have simplified it. So what you can do is you can either simplify this using your calculator or just divide. Go this divided by that. You get 0.00308. So I would have rounded it to that, right? Or 0.31% if they asked you to state it as a percentage. Okay, so that's how you do that. Make sense? For B, how is that going to be different? Repetition is allowed. So probability is NA over NU. And I think right now I'm just going to just say it's 26 squared times 10 cubed. 26 squared times 10 cubed, because you can use 10, 10, 10 back here and 26, 26 up front. That's why I come up with this. And the top It's still 2 times 1, guys, because you can't do SS. The condition is that it has to have S and Q, right? So that's why the top is still 2 times 1, but then I multiply the rest here can be repeated, right? This could be 10 times 10 times 10. So this is 2 times 10 to the power 3 over 26 squared times 10 to the power of 3. I don't know if you noticed this, but technically you could do that, right? That's 2 over 26 squared. That's 26 squared there, 676. Which is 1 over 338, which is, I have 0.00296. I'm just going to double check. Yeah, 0.00296. This keeps going, right? But 4 decimals would be okay there. So that's how you come up with this part. Morning. We good? I appreciate you trying, regardless of what the outcome is. 9. I was asked to do the password, another password scenario here. A 4-digit password, so it's just numbers. So you can repeat some of the digits, but not all 4 digits can be the same. If I could highlight on this, I would. Right? But this is a new. But I briefly talked on it on last Friday about this one here. So we'll talk. We'll deal with that. So this is question 9. Okay, 4-digit password. Oops, I'm going to block this a bit. Can't have all the same. Okay, that's probably a good one to consider. And so let's try A here. A is asking, determine the probability that her password will be greater than 5,000. Greater than 5,000. Okay, so let's consider this. 1, 2, 3, 4. If you want this to be greater than 5,000, the front has to be 5, 6, 7, 8, or 9. Would you agree with that? Yeah. And some of you are saying, well, what if there's a 0 at the end, Mr. Dixon? Isn't that going to be 5,000? It's going to be greater than 5,000? We'll deal with that in a bit. We'll deal with that. So I'm just going to go 1, 2, 3, 4, 5 options here. And then I'm going to go times 10, times 10, times 10. Okay, this is NA, by the way. I'm working on NA right now. That gives me 5 times 10 to the power of 3. 10 to the power of 3 is just 1,000, right? It's 1 followed by 3 zeros. So 5 times 1,000 is 5,000 passwords that I narrowed everything down to the 5,000 here. But here's the kicker. Okay, you gotta subtract one password that ends with 0. Right? The one that would end with a 0, I'm going to get rid of that. Okay. I also have to get rid of a few passwords that would have all the same digits. Right? Because you couldn't have all 5s. You cannot have all 6s, all 7s, all 8s, all 9s. You cannot have that. How many passwords do you have that would meet that criteria? 1, 2, 3, 4, 5. Okay. So 5 passwords, all the same. My camera here is, I'm zooming in, then I have to zoom out. All passwords the same. If you don't mind writing this down, right, it'll be the one that's 555, the one that's 6666, 7777, 8888, 99. If you don't want to do this, I totally understand that, but that's what I mean. Because my password starts with 56, right, I need to get rid of these ones because they would occur, right? So what do we have now? So NA is really 5,000 minus 1 minus 5. That's 4,994 passwords that I would be considering. And so what is NU? That's also a piece of work, actually. So we'll do NU here. Let's do it under here, and then I'll just bring it here. So NU, we're looking at all possible scenarios. So I could start, right, I could have 10, 10, 10, 10, which is 10 to the power of 4, which is 1 followed by 4 zeros. But I cannot have, how many passwords would I not include here? I wouldn't include all zeros, all ones. So basically 10 passwords I could not include here. Passwords, all the same. So 0, 0, 0, 1, 1, 1, 1, dot, 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 right? I can't include those because it could be 0 to 10. Okay, so that's my NU. That is basically 9,990 passwords possible. So my probability is 4,994 over 9,990. Is it? Yeah. Does that match the back? I hope so. 4,994 divided by 0.499 it shows here. You just peek. That's 9A. Yeah, that's the answer. If I turn it into a decimal, that's 0.499. So that's good. For B, what is B asking for? Determine the probability that the first and last digits of our password will be 4. The first and the last are 4. By the way, my universal stays the same. Like once I've determined the universal, where is it? Right there. We're gonna keep an eye on this one, so we don't have to redo it in this case. Probability would be 9,990, and now I have to worry about NA, finding NA. So let's do that. It starts with a 4, ends with a 4. So it means you only have one option there, and then you've got the other two that you need to fill in. So this is times 10 times 10. That would be 1 times 10 times 10 times 1 is just 100. How many do I have to subtract there? When would you have all the same in this case? Just once, right? If they all were 4s, that's the only one you got to get rid of. So minus 1, so that's 99. What does this one stand for? All 4s. Okay. Oops. That's right, guys. So this is 99 over 9,999, and that is the right answer. Checked. For C, my probability is still 9,990. I need to figure out NA. What does it ask for in this case? It asks the probability that the first digit of her password will be odd and the last digits will be even. You gotta be kidding me, right? What's up with that? Well, let's try it. Always try it, like lay it out like this and see what you observe. First even, so 0, 2, 4, 6, 8, and at the back will be odd, right? So 1, 3, 5, 7, 9. You've got 5 options to start. You've got 5 options at the end, and everything in between is anything goes in between, right? 10 times 10. So 5 times 5 is 25, times 100 would be 2,500. Do I need to subtract any repeats? If this is 0, you will never have a 0 back here, right? Because it's going to be odd. So you don't have to worry about subtracting. If this had been 2, you never have to worry about. So whoever writes these questions, they think of those things, right? They want you to think like, oh, okay, like this actually makes it mutually exclusive. Like there won't be an overlap. Okay, so we don't have to subtract. So that's 2,500 over 9,990. And there are your lovely, lovely passwords. Okay. So what I would suggest is lay it out like this. Use the fundamental counting principle when they have all these restrictions. Okay. All right. I'm running out of space here. I'll do one more. 12, right? Okay, we'll do 12. So I'm going way to the back of the booklet because I have no more space. I will tell myself, can I do this here? You know what? I think I might be able to do this. I might be able to squeeze it in. So 12. Let's read it first. 5 friends, including Biljana and Bojana, are sitting in a row in a theater. So 5 friends that are sitting in a row. Determine the probability. There it is again. Not a lot of odds here, to be honest. I'm not that happy with it because then you forget about it. We might throw it in. Probability of them sitting together. Probability of sitting together. I don't know, sitting together and sitting in a row, that should kind of remind you of permutations. And this is grouping. Permutations with grouping. So let's try this. Probability. I'm going to do my classic NA and NU. I'm going to try to make this work here. NU is just 5 factorial, right? If you have 5 people and you want to know how many times you can arrange them, that's 5 factorial. NA is different. Them sitting together, factorial, and this is like the square bracket where you have 5 minus 2 plus you've created one group, so you got to add the 1 there. Factorial that. So this is 2 factorial, 4 factorial over 5 factorial. 4 factorial is 24, right? So 2 times 24 is 48. 5 factorial, 120, right? I'm pretty sure, 120. And that reduces, obviously, right? You can get 4 in both of those. But if you just turn that into a decimal, you get 40% or 0.4. So either one, even the reduced form is the same. We all get the same. Is that so? Okay, this is what I'm trying to say. Read the question and be like, oh, okay. Like in the past, in chapter 4, I would have just asked you how many ways can they sit together. That's all I would have asked you for, right? And you'd be like, okay, that's how you do it. Now it's how many ways can they sit together over all possible ways, where you don't care whether or not they're sitting together. So that's this. Okay. That's A, by the way. And B, what does it say? Them not sitting together? There's a hard way and an easy way of doing this. How would you, if it's 40% chance them sitting together, then there's a 60% of them not sitting together. That's the easiest way, the 60%. But if you didn't catch that, this is how you would have done that. This is gonna look ugly, trust me. I'm gonna go, well, all possible minus them sitting together. This is how many ways there are for them to sit together. Over all possible scenarios. So this would be 120 minus 48 over 120, which is 72 over 120, which is 0.6 or 60%. Voila, right? There you have it. This is 100%. Something happening and something not happening adds up to 100% every time. Okay. Is that so? When you're preparing for these, when you're trying these, just look out, right? The passwords, don't use combinations. When it's combinations, you're making teams, right? Or you're choosing, you're selecting. Okay, that's different. Okay, one of the beauties of probability, sometimes if you use perms instead of coms, or vice versa, you still get the same answer as me. And we don't take marks off for that. Because you know how with perms you count more arrangements, like order matters, whether you stand like this or like this. Combinations doesn't care about where you're standing. But because you're double counting with permutation twice, like your denominator and your numerator, those actually end up canceling each other out, like the double counting. So if that ever happens to you, your friend's like, I use perms, well, I use comps, and you both have the same answer, it actually is okay. It's okay if that happens. But you still got to be careful. Okay. Any more questions? Comments? Concerns? You can always ask me, guys. You come to me if you don't want to ask in front of the whole class. Come and see me. If I can, I'll help. Okay.